guys. I know it's a long start there. Just had to try to get that video sorted out. It looks like it's lagging like hell for some reason on Zoom, and I can't quite figure out why. Yeah, it's just been freezing. It shouldn't be like that in the recording. The recording should be smooth. It's just the Zoom has been problematic. Anyways, so today we'll be doing binary trees, binary search trees. That's going to be the topic of the upcoming quiz, and it looks like the audio's picking up, right? It should be. Wait, no, the audio wasn't picking up. Now the audio is picking up, as it should be. As I was saying, today's tutorial is on binary search trees and binary trees. Excuse all the technical difficulties earlier on. The camera looks like it's kind of evened out in frame rate. Just was trying to sort that out. And that pre-roll video that was playing, I'll play that. I'll post that on my courses, and it will be played later in the session. But first, let's get into actually what is a binary search tree and what exactly it is that we'll be implementing today, and what we'll be seeing a lot of in the upcoming assignment and quiz. So here we've got our slides. Let me just get the right files in here really quick. Boom, boom, boom. Alright, so here we've got trees, binary trees. What is a binary tree? So a binary tree is a lot like a linked list, except for that it's not linear. So a node in a linked list, we know, looks like it's a parent node and a child node, and each parent has exactly one child, right? Well, for a binary tree, a binary search tree, what happens is, instead of having each parent have one child, each parent has two children, and we use some useful rules to say like which parent has which child. Right? So the way this looks in terms of like when you actually have the tree drawn out is, well, a node and recursively chains of parents, or chains of children. In a tree, we've got some terminology which is useful for us. The terminology is, we've got a root node, which is like the head of a linked list. That's the node which all of our nodes stem from. We've got nodes, which are any element in our tree. We've got subtrees, which are like each node is sort of the root of its own subtree, which we'll see. We got traversals, which is how we actually go through the tree. Since the tree doesn't have like a linear order of the data, since the data structure is more abstract, since each node points to two different things, we can't really go through each and every node like we did with a linked list. We have to do what's called a traversal, and we'll go through different types of traversals later on. Then another term we say is height. Height is the longest chain of nodes. Size is the number of elements in a tree. And set is a term we use to describe any data structure where things cannot be duplicated. One of the examples of such a thing is, of course, a binary search tree, a binary tree. Before we get any further into it, did everybody get a chance to see and hear the pre-roll video, like the animation for it, or was that cut off? Alright, assuming it was cut off, I will play that now, and that should explain kind of the concept of it. The reason I do an animation for this, instead of showing it completely live, is that it actually visualizes what it looks like to be using this tree. Right afterwards, we're going to be actually implementing it in code, so before we implement it in code, I find that that's a good way to learn about it. So let's do that now. Let's consider a data structure with a particular set of requirements. It has to be able to be traversed in sorted order reasonably quickly. It has to be able to insert and remove elements reasonably quickly. And it has to be fast to search for a particular element. The most intuitive solution one might immediately come up with is to have a linked list which is sorted upon insertion. What I mean by this is that when you modify the add step of this linked list, instead of inserting to the start or the end of the list, you traverse to the right place in the list and you insert there. For example, we have a linked list of integers which goes 1, 2, 4, 5, 6. We need to insert the number 3. We go 1 is too small, 2 is too small, 4 is too big, that's where 3 goes, before the 4 and after the 2. Makes sense? It's sorted at all times, we always have it sorted. To search, we just traverse through until we find the right number, because it's sorted. We know that if it's if it's going to be larger than the first number, it's going to be further along the list. If the number is larger in the list and it's not there, it could work, but it doesn't seem that fast once it gets really big. Let's take one that's 1,000 length. We have to search quite far through that 1,000 length list to get anywhere. And that might not be optimal. maybe there's something more efficient we could do. And this is when we have to consider the use of our references, our pointers in these nodes, and what we could do with them. Do we just have to have one, or can we have multiple? And can we make some rules about where these pointers point to, which will help us in this endeavor? Well, what if we made our rules such that they helped us traverse this list in the most optimal possible way? And what if we just had a more helpful number of these references? Let's say that our nodes can point to 2 items. And let's make the rule that one of the items is less and one of the items is greater. You'll see very quickly how this can be useful. Let's start off with just one node at the top here. This node will have a value of 5. And let's say that the left node is less and the right node is bigger. So since the left node is less, we want to insert 3. We start with 5. 3 is less than 5, it goes to the left. Make sense? Simple. If the right is larger and we want to insert something to the right, let's say we're inserting 7, and now we have 7 to the right. So it goes 5 and then 7 if you try to find the largest element. To find the largest, you just go right, 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 right. Find the smallest, you just go left, 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 left. It's quite simple to find the largest and the smallest. But you might be wondering, what if I have a number that's larger than 5, but smaller than 7? It has to go to the right of 5, but then what does it do? Well, keep in mind that this is a recursive sort of data structure. Every node has these 2 references. So we go 5, well, 6 is larger than 5, goes to the right. 6 is smaller than 7, so it has to go to the left of 7. So it goes 5, 7, and then to the left of 7 is 6. But now you might be wondering how we can make a useful traversal out of this. How do we get this into sorted order? Well, the sorted order question actually becomes a lot simpler if we consider how our recursion is done. We can traverse the list. It's not actually a list, it's nonlinear anymore. We can't really call it a list. We can traverse our nonlinear data structure, our tree, in such a way that we get into sort order by going left, center, right, or right, center, left. The way we can do this is we can follow through. Let's say we want to go largest to smallest, because that's where our tree right now is a little bit more complicated. It's a bit of a better example. We go to the rightmost node to get the largest for the start. And then what is the second largest? Well, the second largest is going to be what was the center of the subtree that the largest is in. What does that mean? Well, remember this data structure is recursive, so every node can be considered the root of its own subtree. Let's visualize the subtree of just the system with the largest node. That subtree has its center node, its lesser node, and its greater node. But what do we know about the subtree? We know that every one of the nodes in this subtree is greater than the nodes above it, because it was on the right of the node above it. So we know that it must have been larger. Since we know that it must have been larger, we can say that it is indeed all larger. We just have to traverse this subtree in order. And to traverse this subtree in order, we go furthest to the right, then we go to the center, then we go to the left. And remember, when I say in order, I mean largest to smallest. So right, center, left is the in-order version of that subtree. And then we go through every other one of the subtrees, and we go right, center, left, right, center, left, right, center, left, until we get through the whole tree and we get it in the correct order. We go left, center, right if we want the opposite order of that. So if we want smallest to largest, we just go all the way to the left to get the smallest, then center, then right, left, center, right, left, center, right, left, center, right, and we get the smallest to the largest. How do we search? Well, at every step, we simply ask ourselves the question: is the one we're searching for less than or greater than the current node? So if we want to have another binary tree, let's say this one has a root of 0. And then, well, we know that negatives are going to be on one side and positives on the other. That way we can say, is our number negative or positive for the start? And let's say on one side we got -5, on the other side we got +5. Right? That's what our tree looks like right now. And I'm deliberately only telling us about the nodes we can see. We can only see the root, the left, and the right. That's all we need to see. Because we don't care about what's on the rest of the tree. That could be really large, really small. We don't care. We just care about what we're searching for. And let's say the number we're searching for is -3. So we go 0. Is it -3 positive or is it a negative? Well, it's a negative. So we can go, okay, it's towards the side of -5. But it's larger than -5. So it's got to be to the right of -5. So we go center, then we go left, then we go right. And what's the right of -5? Well, in this case, it was indeed -3. And then this sorting algorithm, the searching algorithm, can be applied across the board. To search through the tree, all we need to do is just ask ourselves, is it less than or greater than at every step? And if it's equal, that is a separate case, but it's not much different. We just have to set a condition that one of them also takes in the equal. So one of the sides is less than or equal to, one of the sides is greater than or equal to. So hopefully this made binary trees a little bit more clear and understandable for you guys. Good luck. Hopefully it helps with your coding. The tutorials do cover the coding implementation of a binary tree, and hopefully that'll be useful to you. Thank you so much for watching. Enjoy your day. Alright, so I saw a fair few questions in the chat regarding the stuff in the video, and I'll also be able to address any questions you guys have on the mic about that. The first question I saw was about memory complexity. So some student was concerned that the memory complexity of a binary tree will be too much larger to be practical maybe, or that it was just like, do we care about memory complexity in this class? The answer is that memory complexity is not something we focus on in this class. And the memory complexity of our binary tree is actually not that high, because think about it, each node just has a couple of bytes to store the pointer, maybe not even a couple of bytes, maybe like 1 byte to store the pointer to the next node. It stores very little data. So let's say that each node contains something like an image or a string, something big. To have that extra pointer compared to the linked list, it doesn't add all that much space. Sure, if you have like a million things in your tree, it's going to add a lot of space. But in terms of a tree which is, well, smaller, it wouldn't be too bad, and compared to a linked list, it's also not too bad. The trade-off of a couple of bytes of memory for the speed is probably worth it, but we don't actually care in Comp 250 about memory complexity. It's mostly about just time complexity. Then, in terms of, another person asked, is this a B tree? Probably referring to ECSE 202. In ECSE 202, you do cover binary trees, and they're similar, but you don't cover concepts like depth or, for example, the time complexities of various operations. You don't cover the idea of balancing the tree. So there are things about binary trees that are not covered in ECSE 202, which we will cover in Comp 250. But a lot of the concepts will be reviewed as well. Then there is also the question about, is there any way to get the nodes in the order that they were inputted? So is there any way to get the nodes to traverse the tree in such a way that the nodes come out in the same order that they came in? The answer to that is that it's actually not possible, because when we have a binary search tree, all we know is how the node that we inserted compares to the node of the tree, like the root of the tree, right, or the root of each subtree. We don't know is when we put it in. So if we have a binary tree, like for example, we have like 0 at the top, -1 and 1. We know that 0 went first, right? But we don't know if we put in -1 or 1. We don't know what order those came in. So we can infer some things about the order, but not everything. So no, it's not possible to check the order of the elements. And that's another property of actually a set. That's a term that we may or may not have seen so far in Comp 250, but it's a useful one. In computer science, when we talk about like a collection may take multiple forms. So something like an array list, each item has an index, and you can put whatever you want. Imagine it to be like a bunch of slots, and you can put stuff in the slots. Well, a binary search tree is not really like that. The kind of analogy of having a bunch of slots and slotting things in kind of falls apart. And instead of that, what we have is a kind of a set. Like it's, in set theory or in math, we have a set of numbers, and you can't have the same number twice in a set. The set has no order necessarily. Like it doesn't need to have an order. It just kind of these items are just there. And that's what a binary tree is more similar to. It's more similar in terms of what we may see in math to a set than something like a matrix, if that makes sense in terms of that explanation. Now, before we get into implementation or further slides or anything, are there any other questions about the content we saw in the animation, anything that you want clarified, any conceptual wonders about binary trees? All right, I will take the silence as a lack of questions, and we can move on to something closer towards the implementation of our tree. So transitioning on over, another couple things we want to mention before we get to the spicy implementation is a couple terminologies I'm going to be using. So child node and parent node refer to two different things. A child node is a node which has a parent, so it means it's linked from a different node, and a parent node is a node which has children. Then we have the term of depth. Depth means how far down something is in the tree. So something with a and y'all can join me shortly, 2 p.m. Start. All right. All right. Sorry about the technical difficulties. I'm back on the computer now, and we should be able to proceed much more easily. So as we saw on the phone screen in Vim, the nodes of a linked list are comprised of a element and two references. The references will reference the previous and the next, which are nodes in the tree, which will store, well, some other data. And we have a rule when we build our tree of what goes into the first and what goes into the next. So, if you guys were building a binary tree to sort integers, how would you decide what would be the node, like how would you decide when you add a node, whether it should go to the left or the right node of a given subtree when you're adding it? Like when you're adding a node, how would you do it? What would your algorithm look like? And so how would you guys imagine the pseudocode of an algorithm for adding a node to a tree? We have to compare it to stuff, we have to work with these nodes, and remember the structure of our nodes is that it's got a left and a right child. We don't know really the rule yet, but how would you guys go about adding it, right? Keeping in mind the rule of a binary search tree is that one side has a greater value, one side has a lesser value, we've got a side smaller, a side bigger, right? So how would we go about doing something like that in code? What do you guys think? Okay, that's true. And what if there's already a node to the left or already a node to the right, right? Let's say we're in the situation that we have a tree, it has a bunch of elements, and we've determined, let's say it's smaller, so it goes to the left, but there's already something in the left. What do we do then? Yeah, exactly. So we use a recursive algorithm for this, where we traverse through the tree and we find a place to put our node. But now, how would we go about searching for something, knowing our tree rules? Would there be a big difference between the way we search and the way we add? If we need let's say we have some property of something, let's say like the age of an animal, and we want to find the animal of a given age. How could we do this using a tree? Would it be similar to the adding method? Yeah, exactly. So it's the general structure of most things in a binary tree will be to traverse through until you find the correct element using that structure. So now looking here, I'm going to transition us right on over to our screen capture, where we should be able to see our IDE running. There, my webcam is being annoying, but it's okay. Let's just create a new project, and we can actually get to the code implementation. So we'll do that, and we'll write out our classes, and it should work very nicely. So trees, yes, yes. All right. Stop flashing, you piece of crap. I think that worked. All right. Project, trees, source. All right. We'll create a new Java file. I'm going to call it, maybe binary tree. Now, we've all seen generics, hopefully. We covered those in a previous tutorial. If you're going to be confused by the generics notation, I can go over it again quickly, but yeah, we shall see it there. Again, binary trees. Come on. Why is it not? Yeah, binary trees. All right, perfect. Package shouldn't be package name. There is no package. All right. So public class binary tree. Then we will have a generic, so it'll store things of type E. And what can we do? Is there something else we need to do in terms of the generic and in terms of interfaces to make this binary tree work? So remember, a binary tree can contain any element which, well, what do we know about the elements that go into a binary tree? Are there some rules about the elements? What do we know has to be true about them that might not always be true about every kind of object? Well, when we add to a binary tree, what do we do? What is a core function of adding to our binary tree. You say they have to be comparable. Could you elaborate as to why everything in a binary tree has to be comparable? Exactly, yeah. Okay, and how could we force this binary trees class to only accept comparable items into its, like to only be able to work with compatible objects, right? Because here we say E, it can store any kind of object. Is there something we can do with this E to make it require that the objects are all comparable? Yeah, we can say E implements comparable, or even easier than that, we can say actually E extends comparable. Now that's because E is a generic type, so for generics we just say extends, whether it's an interface or if it's a class. We just say E is comparable and it has to be comparable to E. So this here looks like really weird notation. We might not have seen this before. It's where we have something extending something, which is something, right? It's like a nested generic. What this actually means is that a binary tree can store any E which is comparable to another E, right? All right, that's pretty simple, hopefully, right? That's from our previous sessions. And now we can also create a node class. And node is going to look very similar to our linked list. We're going to say public, or just say class node, because it's inside of the binary tree, class node. And then it's also going to take an E, extends comparable. And a node will have some simple properties. It'll have a node E left, node E right, and a E value. Right, so this is a very core structure of our binary tree. In fact, this is almost enough to have a binary tree. What's the one thing that's missing before we can really consider this to be a binary tree? That's true, but actually, that's not even necessarily completely the case. Because if we want the absolute minimum of a binary tree, the smallest one we can make, just having the node class is fine, because every node is the root to its own subtree. So every node that we have technically is a tree, because by the definition of a tree, it's just something that can have these references. They can all be null, so every node is itself kind of a binary tree. What this actually needs is, yes, the root node, but we have to remember that that's not even completely minimal. But yeah, to make this class complete, we can say it's got to have a node E root, and that was correct. And we'll also want to track our size, because when we traverse, we don't want to go through every single element to count all of them to have our size. We can't just say the length of an array, because there's no array. We actually have to track the size when we add and remove, so we'd have an int size as well. Those are our kind of core things to a binary tree. Now, we can implement our constructor pretty easily as well. Are there any things we have to set in our constructor? Like, what would we do when we create our constructor? Let's say we take a constructor which takes as argument nothing and it just makes an empty binary tree. Is there anything we'd have to initialize, or can we just leave everything blank? Yeah, size equals 0. Great point. So we can do that. We can say public binary trees. I should probably change that to binary tree. And that takes no arguments. And it simply says size equals 0. All right. So that's one simple constructor. Now, to do anything else, we really, isn't it 0 by default? Yeah, it is. But if we had like integer here or something, right? In fact, we could even make this easier. We can just say size equals 0 here. But that's just an example that this constructor doesn't really need to do anything. This is fine. What we need now is an add method. So let's say public void add E element. And this is going to add an element to our tree. So this method is kind of a good example of a recursive method. It's one of the most intuitive recursive methods we can write, I think. And it's quite a good example of how recursion can make our lives a little bit easier when we write code, rather than making them more complicated. This method can be as simple as a couple if statements that are very logical. So first we'll say if our root is null. That's very simple. We just say our root is equal to new node. And then, oh wait, we don't have a good constructor for our node, so let's just do that really quick as well. Boom. So this goes here. code generate constructor value. Okay, so now we have a node constructor, which is pretty decent. And in our node constructor, we can set the value of our current node. So here we can say element. Right? So that's one way that we can do it. That's one base case. Now, are there other base cases that you guys can identify? What would be another base case for this method, recursively speaking? Or is there something we need to do to kind of make this method work better? So this is one base case. After this base case, what should we do? Are there more base cases which we should consider in how we build our tree? Let's think about it. When we're adding to our tree, we explained the pseudocode before. What we're doing is we're saying this. We're saying, yeah, if right is null, that's a base case. And there's another one as well. But what we're basically doing is we're saying, compare current node to root of this subtree. If smaller, go left, else go right. And now here we can say if null, add here, else repeat or recurse here. Right? So this is our general pseudocode. This is what we're doing every time. So we're doing, we're seeing if the root is null. If the root is null, that's fine. What if the input equals root? The input couldn't really be root because the input is a node, or is E, right? The input is the data contained inside of a node. So unless node was comparable and node could be put into a binary tree, we couldn't really say if it equals root. Or if it has the same value. Well, here actually we're implementing a binary tree, which isn't exactly like, it doesn't necessarily follow the set properties. It's not a fully strictly a set. It's just, we could make a set. If we want to make a set, what we can do is say if it's equal. So we say if we want to make a set, we can also say that if element dot equals node dot value, then we say return, right? That's how we make a set. We say if there's already a value that's the same, we just return instead of doing it. So we're just using it as a search. Here we don't need to do that. We can if we want to, but it just adds a little bit of complexity, so it makes the explanation a little bit harder. Generally, it's not a required step. The required steps would just be to do the left, right, and those base cases. But hold on one second, though. Can we actually use this current method as our recursion? Or do we need to somehow create an additional method that we have to use as like a helper? Can we just directly recursively use this? Or do we have to use a different method recursively? Like, do we have to kind of make a hidden recursive helper method? Well, yeah, well, what we have to do is we have to actually make our hidden recursive method. We have to make a method here, which is the recursive sort of version of this. This is just the base case method. This one just checks if we're in the base case. Now here, we want the recursive step. The recursive step of this would look like this. It would be public void add, and it'll also be an E element. And this one will say E element, comma, node E root. But instead of root, maybe, yeah, actually, no, I'll call it root. Because it's the root of a given subtree. So now what we can say is, right, if root is null, right, root equals whatever, right? That's a simple base case that we'll have. This, we should never enter this, so this should never happen, but it's there. Or in fact, no, we should not, we should have a null pointer here. It's better if we're not safe in that regard. Instead, we should say if e.compare2, or element.compare2, root.value is greater than, let's say 0, so I'm not sure if that's less than or greater than. We'll see if it's wrong. else. This is our two situations. So this is if it goes left, goes right. Goes to the left. And this one is for it goes to the right. Goes to the right. So now if it goes to the left, we have to say if root.left is null, then we'll say root.left is a new node with the element. Right, very simple. Else, we do recursion. So else we say add element on root.left. Now it's very symmetrical on these methods in binary trees. We can basically copy paste this code for the other statement, except we replace all the dot lefts with dot rights. So we'll say root.right, and root.right. All right, pretty simple, right? And now here Jordan was asking if we want to compare to the same value, like if we have the same value inside of the current element and we don't want to replace it, if instead we want to make it a set, so we want to make sure that it only contains one of each element. It never contains duplicates. What is the step that we should do here for it? Like how could we do that to add that functionality to our tree? Well, what we could do is we could actually check here as well. Else if, and then create this other else if block. And then here we can say if root.left.element or .value equals element. And then we can quite simply say return, right? So this is if it already contains this, then we go away. So this is how we make sure it's a set. We don't have to do this. This is actually not a necessary step in our binary tree, but it is still valid. Oh, did I forget to? Yeah, too many brackets here. So then I can also copy paste this block to this. This is optional. Again, it's totally optional, but it is still there. So this is optional step, making sure it's a set. Right? Is there any questions about what we've done so far in our add method? Any questions about anything we have so far with this add? All right, I'll take that as no questions. So what we can do now is we can actually create a constructor which takes multiple items in, right? So we can say public binary tree, and here I'm going to use some fancy syntax. I'm going to say we can add any number of elements. So I can say e dot 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 e or elements. So this is saying it's going to be either one or many elements, and that treats them as an array. So what we can say is for element, or for e element in elements add element. So this is now our constructor, which is very similar to what we saw in the card game. So this is very similar to A2. And it builds a tree from what we added, right? So are there any questions about this constructor and the format, like how we're able to use a input of a list of elements, and we're able to fill our tree with those elements using the add method? Would you mind re-explaining E elements? Sure. So this is fancy syntax. This is fancy syntax that just means elements, except it lets you put any argument. So we'll see that in our main method here. So if I make a public static void main string args, we can say that string, for example, string array of items is equal to new string array, and it's going to contain, like, let's say, a B, C. And then here we can have a binary tree string tree is equal to new binary tree. And in our constructor, we can pass items, right? And that works because it's a dot, dot, dot. And we can also pass just one string. So we can say whatever, right? So we can do it in multiple ways, and we can just put a list here. So we can just say, it's just kind of a way to make the arguments easier. So now instead of having to do this items array, I can just take this, paste it in here. And now I've got arguments which can take any number of strings. You know, normally in Java, we can only take in as an argument one thing at a time, or we have to make a list of our arguments. Here, we can kind of add a list of arguments that's as long as we want. Does that make sense? Like, we can throw in an array, we can throw in a single element, we can just throw in a list of elements. It just takes in a ton of things. The only rule is they all have to be of type E, which is here as string. Okay, so now that we create this tree, can we predict what's going to happen to this tree? Like, how is it going to look? What's this tree going to look like? Maybe I'll make it actually easier. So we know it sorts in alphabetical order. What is this tree going to look like? Well, let's try it out. We can run this with the debugger. Or not. Fun error there. All right. Well, let's copy paste our code, make sure everything's okay, and restart the IDE. And then maybe it'll work properly. But yeah, the point of that was I think it shut down improperly when my computer crashed. So it should be root A, then B, then C, and they're all to the left, right? So it's going to make like a chain of those nodes. And that would be correct, yeah. So what we'll see is happen is you're adding larger element to the right, left, not the right, I think. Yeah, I might have gotten my bracket or my like little triangle bracket compare thing mixed up. I usually do that when I'm writing these kind of things. So we'll see though which way it did that in. I'm just going to make a new project for this because it looks like this project got messed up, unless I can make a new module. No, I can't, so I'll have to make a new module. Boom. 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 Okay, new Java class. Okay, finally. We've got them, and yeah, let's see. I might be adding the larger element to the right or the left. Right or left, honestly, doesn't really matter. It's fine either way. Could not start compiling the output path for modules unspecified. Come on. Stop being annoying. That's what happens when the computer just crashes like that. Ugh. Bruh. Sorry about the technical difficulties today. Microsoft Windows, bad OS. Trees. Yeah, okay. Come on. Come on, you can do it. I believe in you. Alright, well, hopefully, eventually, it's going to run. But until then, yeah, you were right about it being like that, with the elements to the right, and maybe I got my triangle bracket here mixed up. If I did, that's all right. We can just change that out by saying here, instead of if root is compared to is less than 0, we could just do if it's greater than 0. That's very easy to change. But yeah, that's that. Then we've also got the option of doing a search. So we'll move right on to the search right now, because it looks like this thing is being annoying. What we can do is we can say public e search, and then we're going to say for, well, that's not very useful. Maybe we should say public node e search, and then we have an e element. And this is going to return the element, or like the node for a given element. And this thing is going to be almost identical to add, right? It's going to be really simple. It's just going to be kind of this code, but we're going to copy paste it and make a few changes. So e element, and let's pass in a node root, so node e root. And instead of doing return here, we just get rid of that else if. And instead of saying new node, we can say if root right is null, we return null. And now if root left is null, we return null as well. And and now we'll also be able to return. This method is in the btree class. We can see the node class is closed here. I just accidentally added it at the bottom. This should actually be here. Yeah. Code. Where let me find my code. No, I'll close the brackets first. I was wondering if you can always access the root by this.root. Yes, you can always access the root by this.root. The difference between root here is this is the root of a subtree. So maybe I should even rename it. Refactory name. Subtree root, right? And then the original root can be accessed with root, like that, right? So that's that. And now we can return search for e comma or element subtree root dot left. And here we can return it at search subtree element dot right. And now we have another else statement here, which is our base case. We can say else if element dot compare or dot equals subtree root dot get value or dot value. Now here we say return subtree root done. Okay, so this is our searching algorithm. It seems that my thing won't run right now because it's just, well, I guess, died in my computer crash. But this one here, I can explain in pseudocode anyways, and I'll just tell you how it runs. I guess you'll have to take my word for it. No debugger for this, unfortunately. But the way it goes is it compares to see the value. It decides whether to go left or right. If it goes left, for example, it'll say if there's nothing there, we return null. And else, let's maybe also put an else here. And if there is something there, we keep searching, right? But also, if it's the same, maybe we shouldn't have an else followed by an else if, huh? These should be in a better order. Boom. Else. Now this else goes for that block. Okay, now it's properly formatted, and otherwise we return null. All right, finally. Oh, what's wrong with this? If it's null, else. Yeah, I'll copy paste this block. Boom. Boom. Excuse the thing there. Now it's dot right. Dot right. Okay, finally. Now, when this runs, it's going to see if it goes right or left. If it goes right, it's going to see if it's null. If it's null, well, there's nothing there. If it's going to be the same value, it returns that node. And if there's still a subtree there, we can just search through it. Another thing I forgot here was saying size plus plus. Hey, don't want to forget this step. All right, there we go. So, yeah, the search will just do that, and that should be sufficient for it. Are there any questions about how this search algorithm runs? I know it's a bit ratchet right now with all the random crashes, but it should still be clear, right? Do you guys see how this method works and how it's able to search for any arbitrary item inside of our tree? All right. I don't know if you have questions on search or not. I guess not. So in this case, we're going to actually go into a quick example of what quiz questions look like in terms of binary trees. I can't give you the exact quiz questions, but I'm going to look at some from last semester and try to give you sort of a rundown of what you'll be expected to know come quiz 5. And on Friday, I'll be getting into more detail on these, doing more of a better implementation of a binary tree, maybe without all the technical difficulties, and I'll try to squeeze in an application of it as well. So looking at, hold on, let me pull up last semester's quiz, and we can see it's going to be 2020 fall, and I'll give you kind of similar stuff, not the exact same, obviously, but you can expect the same content is covered. Let's just get that up and running. I had it prepared before, but of course, the thing crashed. So let's see it now. Yes. All right, perfect. So common questions for quizzes would be, you're given a set of elements and a binary search tree, and you're told how they're arranged. So I'll put this in the comments in here. So let's say given an array, let's say 0, then negative 1000, comma, negative 1001, negative 955, and that. Right, given an array, we insert into a binary search tree these elements. What does the tree look like at size 4? This would be an example of one of the quiz questions you might see on trees, binary trees, this sort of thing. The answer to this question, can anybody give it an attempt? All right, any ideas how we could go about doing this? We have this array. We insert this into a binary tree, same as here, right? This is just following the this constructor. We're just basically doing this. We're saying binary trees tree is equal to new this, and then in here we throw in those elements. So those elements will be 0, 51, whatever, right? So how will this tree look after we run this insertion? That's the question. And in terms of code, what it looks like is we're actually just calling this constructor new binary trees with the e dot 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 elements. This is essentially the same thing. How would you guys approach this kind of question? All right, well, maybe I'll give you guys a start on it, and then you guys could come up with further. So what we're actually doing is we're saying, for, so what we're actually doing is we're saying for every element in this array, for, int I colon array, tree dot insert or dot add I, right? That's what we're actually doing every time we do that. So we're asking what happens the fourth time. So what happens when we add the first 4 elements of this array? Or more accurately, what does the tree look like? What does the tree look like means what are the nodes of the tree? Now, when we're doing this, so one of you guys say 0 is root, so it goes 0, then to the 351 to the right, so 351, and negative 1001 to the left, seems legit, because that's from the order we add them in. But is that the, to the left of 1000, okay, I see. So it would actually be more like 1000 on this side. So could you go on the mic and maybe explain how you came up with this solution to this question?
Negative 1000 would be to the left and 351 would be to the right. And then the next one would have to have depth 2 then, since it came after the first 3. And it has a value less than negative 1000, so it would have to be to the left of it.
Okay, that's great, yeah. So we're following our binary search tree rule. It's the same way that this algorithm works. The search algorithm, we're basically following that, and we're following the add algorithm, and we're seeing exactly how it's going to happen. These questions can seem kind of confusing to you, especially with the first 4 elements. This stuff here is here to trick you and to try to confuse you as to how to draw this tree. But in reality, it is just as simple as running the algorithm in your head, and it's the kind of algorithm which I think can be pretty easily done, like in mental math. You just see the first one we had is the root. Is the next one smaller or bigger than the root? That determines which side it goes on. and then that goes from there. Like it follows from that relatively trivially. So we have that kind of question. Now that's probably going to be the least spicy type of question on the quizzes. So if you have questions about how to do these kind of questions, maybe I can do another example. But they're pretty straightforward. As long as you understand how add works, you'll understand how these work. Now, the next spicier kind of question we have will be this. We'll say, given a tree, let's say we draw it out. Let's say A, here we have B, C, D, E, F, G. Now, F, G, and everything are not necessarily, like F, G are not necessarily their actual, like letter values. They're not sorted by those. That's just some arbitrary nodes, right? So, the question might be something like, oh, actually, G here, I'll do something else, like H, I, J, K. So now the question will be like, how many steps are taken to search for J? So how many, like, what is the depth of the recursion to get to J? Maybe it would be how it could be worded or something like that. So what would the answer to this be? How would you guys think about this? So what is the depth of the search for J? How many times does it recurse? Count the number of edges then? Yeah, okay, so can you explain what you mean by that?
If we know if we know what J is, the value, we can directly go for it instead of looking in every branch.
Yeah, well, we know that we're going to do compare to, right? So we're going to say A compared to C compared to whatever, right? And we can assume that this tree is correctly ordered. We're just running the search algorithm. Right, and I'm sorry. Normally, I would want to use letters that are like alphabetically properly sorted, but it's just that I like didn't want to think about how I could, like, you know, run the adding algorithm. So we're just going to say that these letters are not being compared alphabetically; they're being compared by some arbitrary comparison. And like, oh, how would the search algorithm look on this? The trick about that is that we actually don't care what the values of these things are. What we care about is like what is the path that this algorithm would take in finding an element that was stored here. And the answer to that would be, well, this element is going to obviously be larger than A, larger than C, larger than G, so it's always going to go to the right. Now, how many times does it go to the right? Well, it goes to the right 1, 2, 3, 4, 5, 6 times. So we have to recur 6 times to get to J. That would be a traversal, or like a search traversal to get to J. All right, would that make sense to you guys? Isn't it 5? Well, if we count from the root, then it could be 5. If we count from there, it could be 6. I would say 1, 2, 3, 4, 5, 6. If we count that we start at the root, if we count our initial call as a like part of our recursion, and if we don't count our initial call as part of the recursion, then yes, it's 5 because this actual recursive method is actually called 5 times. You could probably argue for either one. So this is not a great like quiz question. It's probably not one that would be asked, but the same concept applies, right? That's generally how it would run. Now, with this in mind, what would actually be the upper bound of the time complexity for finding an element in a binary search tree? So, question, what is the time complexity? Is the time complexity of finding an element in a tree? You say O of n, where n is the depth. All right, that's a great answer, but could you explain to me why is it useful to have this be O of n? Isn't it also O of n in a linked list? Like when we search in a linked list, isn't also going to be O of n complexity to find any element? So why is a binary search tree called a search tree, and why do we use these things for searches, even though it's O of n? How could it be O of n if, like, you know, we have this less than or greater than rule? You're correct that it's O of n, but I'm just asking, like, how did you come up with it being O of n when this occurs? Because really, when we're creating like a linked list, right, we can just add to the tail, like it's a stack. We can just push to the stack, and we can say that, you know, the tree t is equal to new tree, or like a stack is a new stack, and we just keep pushing to the stack, and that's going to be O of 1 to add, which is faster than a binary tree, and it's going to be O of n to sort, which is, or to traverse through. Okay, so we say it's in one worst case where there will be one long branch. Exactly. So we say it's going to be O of n. Now the follow-up question, of course, is why do we care about trees if it's still O of n? Well, the answer is that usually it's much better than that. So answer is that it's O of n when the tree is awful, when the tree is unbalanced. Unbalanced. It has a long chain, and it doesn't really use its properties. So that's when the tree looks like this, like A, B, C, D, E, then, you know, dot, dot, dot. Like, let's say, yeah, right? So this would be an unbalanced tree. So this will be O of n. This is O of n. But now, what would be the time complexity if we had a balanced tree? So if the tree was something like this, like 1 or 0, then here we have like negative 100. Here we have, you know, negative 101. Here we have negative 99. 99. Here we have, you know, 100, 99, 101. How long would it be this? It would be here. So in this tree, in this nice tree, it would take O of log n, where n is the number of nodes. Yeah, O of log number of nodes. So this, can you tell me, why is it log number of nodes?
The maximum depth will be restricted by, like, because if, for example, each node has 2 children, then the maximum depth will decrease each time. I don't know how to explain it, but it's like a factor divided by 2 to the k.
Exactly, you're right about that, because like I'd say the explanation I usually give is that we have, each one has 2 children, right? So to fill up each level, we need 2 to the number of nodes here. So here for size 1, we've got 2 to the 0 nodes and depth 1, right? Here we've got, for size 2, we've got, you know, let's say 2 to the 1 nodes, or for depth 2, we've got 2 to the 1 nodes, 1 nodes, and depth 2, right? And then here we've got, for depth 3 is got 2 to the 2 nodes, and dot, 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 right? So now we've got here, we've got depth 4. Depth 4 is going to be 2 to the 3 nodes, and then depth n will be 2 to the n minus 1 nodes. So what we actually mean is that to get the number of the depth from a number of nodes, right? So our time complexity is like this. Our time complexity for add, remove, search is equal to O of depth. Right? But so how do we get, so, but we always put time complexity in terms of size, right? So our big O notation is not O of the depth. Our big O notation has to be O of the size. So what we have to say is that depth is equal to, depth is equal to, or depth to the 2 minus 1 is equal to size. But then we can also say that the inverse operation of that will be the depth, and I'm going to drop the minus 1, so drop minus 1 because it just came up from starting depth at 1. And then we say that size, or depth, is equal to log base 2 of size. Right? Does that make sense? Here, if I start this at depth 0, it's going to be just 2 to the n rather than 2 to the n minus 1, and maybe I should do that just to make it more clear. So depth 2, depth 3, depth n is going to be 2 to the n nodes. There. Now it's kind of more logical. Do we understand kind of why that is then? Like, why is it... Do we understand why it's O of n in the worst case, but it's going to be O of log base 2 of n in the situation where our tree is nice and well-behaved? All right. Now, later on in the course, we'll learn how to make trees which actually balance themselves, and that's a big thing in Comp 251 as well. I don't actually know if we'll cover it in Comp 250, but we will be doing it in terms of O of n. Just wondering, if we were asked the time complexity of a B tree, you will be asked about time complexity of a B tree, and in general, you would say O of n for things like add and for things like remove, because it's not specified the tree is well behaved. So here's a question that might throw people off. If we say, question, what is the time complexity of add? Is the time complexity of add for a balanced binary search tree? Now, what is the answer to this one? O of log n. Log n. Right? That's because we know it's a well-behaved tree. We know it's a well-behaved tree, behaved tree as above. Right? Now, if I just said, question, what is the time complexity of search for a binary tree? Asking this, well, what's the answer? It's log n. Well, not quite. The difference here is actually between the idea of balanced and just binary tree. When we just say binary tree, it's going to be O of n, because technically, in the worst case, it can look like this. And by this, I mean like that. Right? And if it looks like this, that's going to be O of n, because we're just going to have to traverse through this entire list and get to the item at the end. If we're technically looking for nth letter, then it's just going to be traversing a linked list, and it's going to be O of n, right? So that is kind of the confusing part of time complexity for a binary tree. Now, I would get into more of these quiz questions right now, but those actually need you to understand how we can use stacks and queues in conjunction with a binary tree, rather than just doing binary trees purely. So next time, what we'll do next time, we'll have stacks and queues mixed with trees, used for traversal. We will have more questions. We'll have remove. We'll have application of a BST, and we'll have a, what else did we not cover? Anything else that I haven't covered today? Today, that will be on the quiz. Now, a couple final notes about the tree. So trees technically don't have to be binary. Trees may have n children per node, but binary trees have two. That's why it's binary. Right, that's one thing. The next thing we want to say is that a graph, which is not what we're doing here, but a graph is like a data structure with links, and a tree is a type of graph. We don't need to know more on that. It's just in case somebody in like a quiz question or somewhere else says something about a graph. That's what we mean by that. Then another thing we want to cover will be the different types of search, which we will cover more next time, but I'll give you a quick peek of the slide anyways. So there we are. We go, the root is of course each node, and we've got in-order traversal, which goes through each of the roots to get them in sorted order. We've got reverse order traversal, which goes through in the inverse of the in-order traversal. If we use a stack for in-order, we can use a queue for reverse order, and then we can use the same algorithm, and just if we push to a stack versus a queue, we can get it in opposite orders. We have a search algorithm, and search will use the property, as we did today, to find each element. Breadth first will search through the width of the tree, like through the trying to get through each level of depth before it goes to the next one. And depth first will go to the deepest possible depth before iterating to the next. That should be most of the content we care about in terms of those trees. A quick note that the next assignment will also be heavily about these, so it's good to understand like a good mastery of the trees. Usually every semester the tree assignment is the hardest one, so it is something to be prepared for. But anyways, hopefully it shouldn't be too bad if you guys really understand the content. And are there any final questions about anything?